Recording is rolling. It is Monday, December 16th. So do all this right here. Right, midterm schedule. You guys know I posted this to Google Classroom about a week and a half ago. So you guys have that. But let's get a closer look. So you guys know today's a regular day. Tomorrow is your first exam. It's going to be first period. Oh, look at that. 2 hour block class right there. 2 hour block class. It's first period. Guys, which class do you have lunch with tomorrow? Fourth period. Ooh, probably good to know what you have. Like here, I could say for myself, I have C lunch, right? So for any of my classes that matters, because I'm doing a recording for all my classes right now. I have C lunch myself. Okay. How about on Wednesday? Who do you have lunch with? Here, the third period class. On Thursday is fifth period, which usually fifth period. Anyway, how about Friday? Who do you have lunch with? Seventh period. Right. So again, I know I have C lunch myself. Figure out for all your classes. All right. So you guys got it. Midterm schedule, lunches. All right. Ooh, AP equations. So back in August, I gave you guys the old AP equations that they've been using for about 10 years now, but this is the updated version. So this one's new. Right. There's a lot of overlap, but there's a few different things. So let's go over it. The first three formulas here are the three kinematic formulas. Look at that, three kinematic formulas. Now, I write them a little bit differently than AP writes them. For example, I write X as displacement, like a change in location. AP writes X as position. So they have final position equals initial position plus B on T plus half AT squared. Okay. A few other little differences, but you can kind of tease out the differences. Different textbooks, different ways. Here's, center of mass. You guys remember center of mass? I think I got it. Here we go. You guys remember it's like a weighted average of masses. So mass times location, add them all up, then divide by the sum of the masses, gives you the average location. So you guys seen that? And then here, while I'm on that one, if you go all the way down to the very bottom, you guys see the momentum version of that? The sum of momentum divided by the sum of the masses gives you average velocity, the velocity of the center of mass, I should say, right? All right. So this and this actually go hand in hand. All right. We got, hey, it's Newton's second law of motion. Acceleration is net force on total mass. Here's universal law of gravitation. Force equals gmm over r squared. Here's friction force is coefficient of friction times normal force. Now, it's an inequality because if it's static friction, it builds up to that. But if it's kinetic friction, you can just say equals. Hey, here's Hooke's law, F equals kx. Now, AP decided to throw a negative sign, and that's because they're talking about the restoring force rather than the applied force. Oh, here's centripetal acceleration, actually. V squared over r. Got that? The next few formulas are all energy formulas. We got kinetic energy here. We got work is force times distance here. We got work energy theorem here, right? The work you do on something translates into kinetic energy as long as there's no height change. We got energy stored in a spring, 1/2 kx squared. A bunch of these you'll see in the Kahoot we're about to do, including that one. We got a couple of formulas for gravitational potential energy. Here's the universal form. Here's the localized form that we use a lot more often in MGH. Power is work over time, right? Energy transfer per time, right? Rate of energy transfer. Got power. Do you guys remember that elevator poster at the elevator being pulled up at some speed? What's the power of the motor at the top of the elevator shaft? That'd be force times speed, right? FV. Momentum. Look, momentum is mass times velocity. I think it's the last topic we studied right here. Look, they put little arrow vectors above the vector variables, the P and the V. Do you guys remember that impulse formula? So mass times change in velocity results from a force applied for some time interval, force times time. Okay. Now, if you take that and rearrange it and solve for that force, it looks like Newton's second law of motion, doesn't it? So the rate change in momentum is Newton's second law of motion, F equals ma. Right? It's very little bit. Yeah. You guys see a capital J right there with the arrow over it? So that also represents impulse. I haven't seen that in a few years. So AP starting to use that. So delta P, the change in momentum, is capital J impulse. And you get that by applying a force with some time interval. There you go. All right. Okay. Talk about that one. Guys, look at these three right here. It's the kinematic formulas as it applies to a turntable. You guys remember turntable physics? Right? Then right below that, right, I think this is going to show up later today. Guys, look for a bunch of these posters later today. You guys remember that turntable poster? I've got somewhere in the stack that shows the relationship between angular motion and linear motion. So here's two of the formulas. Here's the velocity version and the acceleration version. If you go down about halfway down the page right here, bam, here's the displacement version of that. So turning a turntable, how far does something move? how far the turntable turn. Okay. A specific version of this is circumference equals 2 pi r. That's one round trip. Right. All right. Let's go back. All right. Now the rest of these formulas we haven't quite hit yet. So here's a batch of rotational dynamics formulas. We got torque, rotational inertia, angular momentum. We'll talk about all that in January, but that's not on the midterm. Then here's some oscillation formulas. So like a pendulum swinging back and forth or a block on a spring. So that'll also be next semester. And down here at the very bottom are a bunch of fluid dynamics, which for AP, they just added this. So this just showed up in AP exams starting this year. Okay. So fluid dynamics. So maybe Archimedes principle, Bernoulli principle, Pascal principle, conservation of flow. That's all. All right. So none of that's all going to be on the midterm. All right. So that's the new AP equation thing. Now, since you guys know the midterm is going to be open notes, let's have a really broad definition of notes. So this can count as notes. Anything you've been taking in your notebook, that's notes. Any pages I gave you guys as notes. Let's say your old quizzes, that's notes. Okay, so all right, you guys ready to start this Kahoot? All right, let's get going on Kahoot. Oh, look at you guys go. That's all ready. All right. You guys have a calculator out. You guys have some paper, pencil out. Take some notes here. This can be notes if you're taking notes. You can make some notes right now. A plane flying north at 40 meters per second enters into a crosswind blowing east at 30 meters per second. What's the plane's ground speed? Ooh, oh, okay. Let's get a closer look at that. Okay. So here's my plane right here. Here's my plane. Okay. It's flying. No, it's pointed straight north and it's trying to go straight north at 40 meters per second. Now that's the plane relative to the surrounding air. The propellers can just push against the air. But what about the air relative to the ground? Well, that would be the crosswind. Notice I connected these vectors tip to tail. Hey, I just created a what triangle? 3, 4, 5. You guys see a 3, 4, 5 proportion triangle? Okay. Now, if it was any different numbers, you could use what theorem to solve for this? Pythagorean. Okay. Because I want to know what's the plane's ground speed. Here's the plane relative to the air. Here's the air relative to the ground. Here's therefore the plane relative to the ground. You go tip to tail. So tail of the first vector to tip of the last vector. Pythagorean theorem. You guys can do Pythagorean theorem, right? Okay. A squared plus b squared c squared. Where's my poster to back that up? Where are you? It's right here. Pythagorean theorem. You guys just did that? Okay. All right. Next question. Ooh, we got some points. Got some points. Lots of points. Same scenario. What's the direction of the plane's motion? Yeah. Ooh, key winners. 37 degrees east of north. Let's see how to get that. So if you know geometry of a triangle, say you know the sides, like Pythagorean theorem, we just did that. So we know all the sides of a triangle. How do we figure out the angles? So if you ever want to extract an angle, you have to apply a what on the calculator? Yeah, in inverse trig, right? So for example, you guys see this box right at the bottom, this blue box? I did an inverse tan. You know, if you decide to do inverse tan, you're going to play off the two legs of the triangle. Isn't that right? Right. So let's go back to the plane scenario right here. Here's the plane. Okay. Here, 40 meters per second north, 30 meters per second straight east. Okay. So I can do here this angle right here. If I do inverse tan, that'd be opposite over adjacent. That'd be 30 over 40. Try that in your calculator. Guys do inverse tan, so second tan to get inverse tan. 30 over 40. I bet the calculator says something like 36.87 degrees. Is that what it says? 36.87 degrees? Right. I'll call that 37 degrees. Right. Okay. So you guys know how to extract an angle from a right triangle? All right. How are we doing on points here? Got Jonathan, La, Elise, Zach, Peyton. Ball dropped off a cliff. What is the speed of the ball 5 seconds into falling? Set the second kinematic formula right here. Oh yeah, there you go. All right, here, close over. Right. So, if you're asked, if you drop a ball, guys, drop a ball means what variable is equal to what? Initial velocity is equal to 0 if you drop something. So anywhere you see it be not, like here, if you just call it 0. Okay. If you're asked how fast is something moving as a function of time, well, that's the second formula right here. So you did 10 meters per second squared, because Earth, that's implied. 5 seconds gives you 50 meters per second. Right, you guys do that? Right, guys good? Right. Well, I got this. Let's look at the graph versions of dropping a ball off a cliff. Here's dropping a ball off a cliff. How far, how fast, and acceleration. Graphs look like that. Okay. And here's the table version of the graphs you just saw. Okay. Ball is dropped off a cliff. How far does the ball fall in 5 seconds? How far? R is a function of time. Hey, does that sound like h equals 1/2 gt squared? Huh. Whoa! How'd everybody know that? College. College is the answer to that question, because that's the college equation, isn't it? Here, if I go back a couple of posters here. All right. Here's the full formula you could use to solve this first one. Here's how far is a function of time. Okay. Here, we got how far is a function of time, how fast is a function of time, how fast is a function of distance. Here's back to how far is a function of time. Drop the ball, v naught 0, so this goes away. I can say h equals 1/2 gt squared. Okay. So you plug in 10 meters per second squared here, plug in 5 seconds here. 5 squared is 25. Half of 10 is 5. It's about 125 meters deep. Hey, how'd you know that? College. College. La Elise, Jonathan, Zach, Peyton. We gotta get the graphic on this one. Here, I'll walk you guys through this. So here I got 100 Newton weight. You guys see this weighs 100 newtons? And the left force times sine of alpha is 30 newtons. Okay, so do you guys see this little green component right here is 30 newtons. So the question is, what's FR sine beta? Oh, that would be this upward component right here. So 100 newtons pulls straight down. 30 newtons is this little bit right here. What is this big guy on the right side? You guys see the principle is that the force has to zero out. So it's 100 down, got 30 up here. So what's going to balance it out on the right, on the other side? Yeah, 70. Okay. So here, point that out again over here. Okay. So it's 100 newtons down. This little bit here was 30 newtons because it said FL sine alpha. Okay, well, that wouldn't be this component. It's 30. So this has to be 70. You guys think 30 and 70 up balances 100 down? That's this green condition right here, right? Okay. So we got 3 either vectors or components, 2 up, 1 down, and they all have to zero out. All right, guys good? La, Olivia, Elise, Zach, Peyton. All right. Another one of these. So this time, this left component, FL cosine alpha, that's how much to the left. Let's call that 70 newtons. Well, then FR cosine beta, well, that would be how much does this one pull into the right? So if left is 70 newtons, then what is the right component equal to? So the guiding principle is this blue equation here. The sum of the forces in the x direction has to zero out. So 70 left, 70 right would cancel out with that. 70 plus negative 70. No winners. No winners. Let's take a look here. Okay. So guys, I said FL cosine alpha, that's this blue component right here, is 70 newtons. You see it? This is 70 newtons to the left. Right? So there's only one other horizontal component, which is this one to the right, which has to be how much? 70. Okay, 70 to the right and 70 to the left. Isn't that sum to 0? Okay, that's what this says right here. Sums to 0. Okay. Atwood time. You guys ready to solve an Atwood? 9 kilograms versus 8 kilograms. What's the acceleration? 9 versus 8 kilograms. What's the acceleration? All right, you guys got that? Let's walk through this. So, got my classic Atwood. This massless frictionless pulley is being held in place. Okay. Here's the guiding principle: is Newton's second law of motion. Is whenever you get how much acceleration, well, there's two approaches. There might be a kinematic approach if you're told about the motion of something. But if you're given forces and masses, that's Newton's second law. Okay. Now, you go to college, you might have a teacher that possibly starts with these two green boxes, but I'm going to say this for last because I've always been solving this with you guys through a whole system approach. So I'm going to look at this as a whole system. So here's 9 kilograms on this side, and here's 8 kilograms on this side. So let's figure out the external forces driving the motion. How much weight is this right here? 90 newtons. How much weight is this right here? 80 newtons. Okay. And we've got a competition clockwise versus counterclockwise. So I'll set up Newton's second law. Acceleration is net force acting on some total mass. Okay. So, guys, clockwise versus counterclockwise. What is the net force? 10 newtons. Yeah. 90 newtons minus 80 newtons is 10 newtons net force. Okay. How much total mass is being moved around? 17 kilograms, right? 9 kilograms plus 8 kilograms is 17 kilograms. I got 10 newtons net force moving 17 kilograms. 10 on 17. So 10 newtons net force, 17 kilograms. That's 0.59. Oh, newtons per kilogram. Is that called meters per second squared? Same thing. There you go. There's the acceleration. You guys got that? Oh. I got a sort of follow-up question for you guys. Do you guys think the string, this connecting string, has some tension in it? Could the tension in the string be 500 newtons? Or is that way too much? I think it's 500 newtons? I think it's way too much. Could it be 10 newtons? I think it's way too small. Because the tension in the string has to be between what and what? 80 and 90. Yeah, because the small block has to be driven upward and the large block has to be able to fall downward. I'm going to guess maybe about 84, 85 newtons. And you can find out exactly by focusing on one block and solving one of these. Go. I got Jonathan, Alexander, Elise, Zach, Peyton. Block slides at constant velocity. 5 kilogram block, 30-degree incline. What's the coefficient of friction? So help you guys out here. If I had you guys solve this from scratch, which my AP kids, I definitely want them to be able to solve this from scratch. It's a whole process. You guys see this whole process? But to give you guys the quick synopsis, constant velocity, is that equilibrium? Yeah, that's equilibrium. The forces have to sum to 0. Therefore, I know mg sine theta right here has to be equal to the friction force. mg cosine theta is equal to the normal force. You do all this math. Here's the end result right here. The coefficient of friction, this was the lab you guys did, is very simply tangent of the angle. Can you guys do tan 30 degrees? Right, tan 30 degrees, because that ends up being the answer. Right, now it's kind of a shortcut, but my AP kids especially, I want them to be able to know that process. Okay, so you guys got that? So if there's ever a block sliding down at constant velocity, just like the lab you guys did, I think you guys set up some lab weights on either a book or a desk. Different classes did it a little bit different. Okay, as long as it was constant velocity, you say, oh, tangent of the angle. That equals the coefficient of friction. You guys notice the mass of the block canceled out. That's not part of the calculation. Okay. All right, Jonathan, Alexander, Zach, Elise, Peyton. Block slides without friction, which means it's going to accelerate. 5 kilograms, 30 degrees. What's the acceleration? Okay. Now this one's a shorter proof. So it goes like this. This mg sine theta component right here is the net force that's acting on a block mass m. The m cancels. So the acceleration is very simply g sine theta. So can you guys plug in 10 meters per second squared times sine of 30 degrees? Oh, speaking of which, guys, what is sine of 30 degrees? Yeah, 0.5 exactly. So what's half of Earth gravity? So that would be the answer, wouldn't it? All right. You guys remember your Hot Wheels car lab? Right? You took some Hot Wheels cars, let them roll down the incline. I bet if you took Earth gravity times sine of the angle of that incline, that would give you how much those cars were accelerating down the incline. Pretty close to. Okay. Aha. All right, so you guys doing good so far. Doing good. Everybody's doing good. All right. All right. So winners. Ooh, turntable time, 9 radians per second. What's the linear speed of a coin 14 centimeters from the center? So 9 times 14. Right? All right, so this is one of those posters that was going to show up later. Right. I think it was on this AP page. You guys remember? Oh, we're looking at these two right here. I'd say halfway down the page is this one, this displacement version down here. All right, here they all are. Displacement, velocity, acceleration. Okay, so we got angular motion, radians per second, radians per second squared, and tangential linear type motion. How far, like meters per second squared. All you have to do is multiply by your location from the center. You go from one to the other. I just did this one right here. That times that equals angular velocity times distance equals your tangential velocity. All right, guys got that. What is the angular speed of O'Neill cylinder with radius 1,000 meters so that the target artificial gravity is 9.8 meters per second squared? So you see this one at the bottom right? So your target acceleration is 9.8 meters per second squared because gravity field is an acceleration. Now, of course, there's no real gravity anywhere around, but you give this thing a spin. Okay. Go ahead. All right, let's get a look at this one here. All right, so here's your O'Neill cylinder. All right, we're targeting 9.8 meters per second squared right here. So I'll tell you, 9.8. Okay. Of course, around deep space, if it's not rotating at all, is everybody just floating around like an astronaut? Yeah. Now you give this thing a spin. Okay. Now, everybody on the inside surface, remember they want to move in straight lines, but there's a wall holding them there. So now the wall pushes against them with a normal force, and they experience that as an artificial gravity. Okay, like that. So I need to figure out, I'm going to target 9.8 meters per second squared. I'm going to divide by the radial size, which I told you guys was 1,000 meters. Okay. And then to solve for this angular velocity, what's the very last algebra step I have to do? Square root. Here, I'm going to do it this way. I'll scroll to the beginning, second, insert square root of all that. Okay. And this answer is always going to have units of radians per second, not revolutions per minute or any other unit. It's going to be radians per second naturally. Okay. 0.099, is that basically 0.1? Yeah. So 0.1, and then that would be, radians per second. All right. Whoa. Hang on, my screen's all wonky. Let's try this again. All right. All right, so you guys good? All right, if you guys have any questions on these, let me know. All right. I got Jonathan, Alexander, Elise, Zach, Peyton. Oh, all right, this one's a little weird. Two satellites orbit two different planets at the same radial distance. If a large planet has 3 times the mass of the small planet. Right here. Do you guys see this orbital speed equation? Now, my AP students, I want them to be able to derive this from scratch. But for you guys, let's just jump straight to the proportion. So we got the same radial distance, same universal gravity constant. Let's start with, guys, what is 1 times 1 divided by 1? It's 1. Square root of that is just 1. So let's say that's the first planet. Okay. The next one, I got 3 times the mass of the planet. So what's 1 times 3 divided by 1? And what's the square root of that? Because what's the square root of 3? Right? That's a quick way you can navigate proportion questions. Just make everything 1, and the answer is going to be 1. And then change, in this case, mass by a factor of 3. And the answer is the square root of 3. Right? You guys see that? Right? If you used realistic numbers, like we're going to make G 6.67 times 10 to the negative 11 meters squared per kilometer squared, right? You plug in like actual numbers, you still get this exact same ratio. Still square root of 3. Okay. All right. On fire. If a moon took 3 times the time to orbit a planet as previously thought, okay, it takes a day. Oh, wait, actually, it takes 3 days to orbit. Whoa. That tells you something about the mass of the planet. Here's another proportion question. So, guys, what if all this numerator comes out to 1, and then g times t squared is 1, so the whole thing is 1? The mass of the planet is 1 mass unit, whatever. Right? Wait a minute. Actually, we saw that wrong. The time for the moon to go around is actually 3 times as long as we thought it was before. Let's throw a factor of 3 on that t. Now that's going to get squared. 3 squared is what? Okay, and then that's in the denominator, so it's 1 over that, right? I think the fact that it's taking this planet longer to go around because the planet is not nearly as massive as we thought it was to begin with. It's a lot less massive. How much less massive? Yeah, 1 over. So 1 over 3 squared would be 1/9. Okay. Okay. So proportion type question. All right. All right. Jonathan, Alexander, Elise, Zach, Peyton. Throw a ball straight up at 10 meters per second. How high does the ball go? Five meters. 5 meters. Okay. So let's try this out. Okay. Oh, here's 2 different ways to solve it. You can start with the third kinematic formula. You can start with conservation of energy. Either way, you get to this box. Here's how high does the ball go as a function of how fast did you throw it. Okay, it's the same answer. Okay. So I said you throw it at 10 meters per second. Try this out in your calculator. Do 10 squared. Guess what's 10 squared? 100. Okay. And then 2 times, well, it's implied we're on Earth. So what's 2 times Earth gravity? That makes like 20. Okay. What's 100 divided by 20? 5 meters. Boom. Right. The reverse version of this question could be, suppose you know how high it goes. How fast did you throw it to get it there? And that's this expression right beneath it. Square root 2gh. Oh, which keeps showing up over and over again. Okay. How many guys also noticed that, let's see, if you throw a ball up at 10 meters per second, it goes 5 meters high. Hey, what if I did that exactly backwards? What if I went to the top of a cliff and dropped a ball? Guys, after 1 second, how fast is it moving? 10 meters per second? And how far did it fall in that same time? 5 meters. Isn't that, hey, that's exactly the reverse of this. This is the ball falling. This is you throw the ball upward, but it's the same numbers. You see that? You guys good? All right. Of course, you could use those. Okay. Kinematic formulas, conservation of energy, different ways to solve that. Jonathan, Alexander, Elise, Peyton, Zach. Galileo drops the ball off a. Oh, that right there is the height of the leaning tower. I looked it up. 55 meters. What is the crash speed? All right, so square root of 2gh. Here, okay, let's look at that one too. Okay. So, here, this is one that keeps coming back over and over and over. Next semester, we're doing fluid mechanics, Bernoulli principle. This will come back again. It'll be the same answer. The speed of anything you drop off a tower. Square root 2gh. So square root 2. Earth gravity is 10 meters per second squared, about. And the height of the leaning tower is 55 meters. Put it all together. Yeah, 33 meters per second. That's the crash speed right there, 33 meters per second. Okay. Isabel, Alexander, Zach, Elise, Peyton. How much energy is stored in a compressed spring? Yeah, the area under force versus distance graph. Okay. So let's look at this graph again. Okay. So got a spring. Now so you can compress a spring, you can stretch a spring. Either way, take some force, take some energy to do that. There's different concepts with different units, right? Newtons versus joules. Okay. Here's a graph, force versus distance. Now, notice it's a non-constant force. It's a variable force. The more, like if you're stretching it, the more you stretch it, the more force it takes to stretch it more, right? So it goes like this, F equals kx. That would be an ideal spring. Guys, what does the slope of that spring represent? The spring constant k, right? Does this look like y equals mx, right? F equals kx, right? Y, x, fx. Right? So that's how stiff the spring is. Right? If it was steep slope, it would be really stiff. Not too steep, not too stiff. Okay. And then the accumulated area under the curve. Hey, that's this green triangle. You guys see this green triangle? That was actually the Kahoot question. Is how much work does it take to either stretch or compress the spring? How much work does that take? Right? Which is also therefore how much energy is stored in the spring. Same number of joules. It's this green triangle right here. Okay? So the area under the curve, force versus distance. You guys good? You guys gonna get those? All right. Isabel, Zach, Alexander, Peyton, Elise. Car burns 1 gallon of gasoline to go from rest to 10 meters per second. How much gasoline to go from rest to 30 meters per second, which is 3 times the speed? Help you guys out here. 3 times the speed is how many times the energy? 3 times the speed is how many times the energy? 1/2 mv squared. If you triple the speed, and you square that, that's how many times the energy? 9 times the energy. Okay. I know a gallon of gasoline has some quantity of energy in it. Yeah, you would need 9 times the energy. That's 9 times the gasoline. Right, 9 times the gasoline. Right. Because another version of this question is if you're braking to a stop. So suppose there's 2 cars and they're the same, except one car is going 3 times the speed of the other car. If you're going 3 times the speed, how many times the braking distance is that? Also 9 times, right? 9 times, right? Which you just saw on that poster too, right? Okay. All right. So I know 3 times the speed is 9 times the braking distance. Okay. Next question. Two cars, same speed. One car has 3 times the mass of the other car. What's the braking distance? 3 times the mass. Uh, same distance, same braking distance, same braking distance. All right, so let's look over here. All right, so you guys just saw a couple of questions related to car braking to stop. Right. Now here, how I'm solving this is with an open system. Guys, the car has what kind of energy at the beginning? So kinetic energy, 1/2 mv². Right? By the time it comes to a stop, that's zero energy, zero mechanical, and it lost it work done by friction, so force times distance. Right? Right, so you do, well, there's a couple substitutions here, kind of skip, but it works out. So the braking distance ends up being this expression right here. So the initial speed of the car squared divided by 2 times the coefficient times the gravity field. Now, going back a couple of questions ago, if you're comparing speed and braking distance, do you guys see if you have triple the speed, this is going to correspond to 9 times the braking distance because 3 squared is 9. Okay. So the question you just answered with Kahoot said 3 times the mass of the car. And earlier this semester, I think I phrased it like if you have an empty car versus a car full of groceries. So you change that. You guys notice that the mass canceled out? By the time you get to this expression, mass is not part of that expression. So it doesn't matter what the mass of the car is. Now, more mass would be more braking force, but it ends up canceling out. So the braking distance ends up being the same. Yeah. All right. Is that okay? Yes, sir. All right. What is the reading on the spring scale if the weight is 300 newtons? Yeah, 100 newtons. All right. All right. Nice. So this weight right here weighs 300 newtons. Let's see, 1, 2, 3 strength. So the weight got split 3 different ways. Okay. So the tension is now 100 newtons. Okay. And that's the force you have to pull with on the side of the spring scale to lift it. 100 newtons. So now you're effectively 3 times as strong. Yeah, you have 3 times the strength now because of that simple machine. Peyton, Isabel, Zach, Alexander, Elise. Ooh, great race. What happens to kinetic energy of a system due to the inelastic collision? Inelastic, look, they stuck together. If you compare kinetic energy after compared to before the collision, kinetic energy always does what? Make it any set of numbers you want. Yeah. As long as the objects stick together, you'll always get what answer. Ooh, decrease, right? So, yeah, if you run 1/2 mv² before the collision and after the collision, that kinetic energy always decreases if they stick together. Now, guys, a lot of you guys picked the gold one here. Kinetic energy is only conserved for what special kind of collision? Elastic. Yeah, elastic, which is perfectly bouncy, which is on the other end of the spectrum from inelastic. So, guys, here's a full table right here. Right. Let's compare elastic to this inelastic here. Elastic, they bounce off each other, and yeah, kinetic energy would be conserved there. But perfectly inelastic, where they perfectly stick together, right? Yeah, well, momentum's conserved, but that's true for all these. But kinetic energy always goes down, always less after compared to before. What do we do here? Got Peyton, Zach, Isabel, Alexander, Elise. A ball, 0.15 kilograms, so that's a baseball, sits on a tee. It's hit with 500 newtons force per 0.01 seconds. How fast does the ball leave the tee? Just got that. All right. Let's bring this over here. And so impulse formula. So I told you an average force of 500 newtons. Allows for 0.01 seconds because bam, so real fast. Okay. So there's the impulse. You got an impulse of what, 5 units, it looks like, 5 kilogram meter per second. Now, if I divide by the mass of the ball over here, divide by 0.15 kilogram, baseball, you give me the change in velocity. So I got a change in velocity of 33 meters per second. Okay. There's one more step. If the ball starts from rest, then this change in velocity would also be the final velocity. Okay. All right. All right, you guys, all right. Everybody doing all right? All right. Mass of the pitcher, 50 kilogram. Mass of the ball, 1 kilogram. Speed of the ball, 50 meters per second. No friction. What's the speed of the pitcher? Hey, it's Magic School Bus. Magic School Bus. So I got a 1 kilogram ball going 50 meters per second to the left. Okay, presumably they started from rest on top of the mound. Okay. The pitcher is 50 kilograms, sliding how fast to the right? So momentum's conserved. Okay. So do you guys think 1 times 50 to the left is equal to 50 times what to the right? Yeah, 1 meter per second. Right? So 1 times 50 to the left equals 50 times 1 going to the right. Right? Because it all zeroes out. So momentum is a vector. So the momentum is always 0. Okay? So it all cancels out. Okay? You guys, here's an extension question. So these velocity values are relative to some nearby tree. Okay? That's not moving at all. Okay? But what if I actually something a little different? What if actually, how fast can that pitcher actually throw the ball? Like if the pitcher was planted into the ground, what's the actual throwing speed from the pitcher? "51 meters per second, right? Because isn't the ball relative to the pitcher? Actually, okay, it's going 50 meters per second forward, but that's relative to some nearby tree or relative to the catcher, right? Okay. The pitcher is going 1 meter per second back the other way. Let's call it like negative 1 meter per second. Guys, what's the difference between 50 forward and 1 backward? That's 51. Right? Okay. So the pitcher is actually throwing 51 meters per second. That's a little twist on that. Okay. If you ever see something like that. Okay. Like I know my AP students had a question recently on their AP questions, like if somebody's walking on a plank out in a lake, as they walk forward, the plank's being pushed backward. So you say, well, okay, they're walking how fast relative to the shore or relative to the plank, because that's 2 different velocities. Okay. All right, got Peyton, Zach, Isabel, Alexander, Elise. Bullet and bounce ball fired with equal momentum. Which collision makes the bowling ball roll faster? Yeah, that elastic collision, the one where boing bounces off, because that one delivers more impulse because there's a greater change in momentum of whatever's colliding with the bowling ball. So it can transfer more momentum by elastic. Yeah. Oh, here I got posters to back all these up. Where's my bounce ball poster? Oh, maybe I don't have that one up. But you guys got this question coming up. All right, you guys ready to solve a ballistic pendulum? We got Peyton, Zach, Alexander, Isabel, Elise. All right, I think it might be ballistic pendulum time. Yeah, there you go. So I gave you the mass of the bullet, the mass of the block, the gravity field of the planet, and the height change. Find the firing speed of the bullet. You guys have 2 minutes, but I'll walk you guys through this. So if you solve this from scratch on a blank piece of paper, here's what's going on. The bullet's fired into a block. Want to figure out what's the firing speed of the bullet. First of all, there's a collision. That sounds like conservation of momentum. Then the whole system swings up to some height change. That sounds like conservation of energy. Okay? Now we're going to solve this chronologically backwards, like reverse chronological. So I'll start with that height change right there. I'll say, well, if it started, some kinetic energy got it in motion and it went up to some height, that's potential energy. Okay? You can solve for how fast was it swinging at the bottom. How fast was the pendulum at the bottom? No surprise, it's square root 2gh, because that keeps showing up over and over again. You guys did a whole lab on just pendulum speed. You do that. Okay.
But how did it get going that fast? Well, because the bullet collided with the block. That's what got it going that fast. So now we're going to go from this green box, which is energy, to this gold box, which is momentum. Momentum is conserved. So all the momentum was coming initially from that moving bullet, mass times velocity of the bullet. Okay, so now we got something we can solve for this speed of the bullet. The bullet and block collide together inelastically and get going at some speed. How fast? Oh, well, that's what we do all this energy stuff for. Here's your square root 2gh right there. So there's one algebra step away from getting the answer. Just divide by the mass of the bullet. Okay? Now, I gave you all these numbers, so let's plug them in. So 1 kilogram on the block, 0.01 kilogram on the bullet. So this combined mass is like 1.01 kilogram. Okay? Square root 2gh. So that's square root 2 times 10 times 0.29 meters. So you got all that. When you get all that, last step is divide by 0.01 kilogram mass of the bullet. That will give you the firing speed of the bullet. Okay. Now, since this is going to be open notes, if you guys got this lying around, I mean, the answer is right there at the end. You just plug everything in. All right. Yeah, so you should have gotten 243 meters per second. Oh, I'll do that on my calculator screen also over here. So you guys get another look at this. Here we go. So the answer is just this very last line. I would just walk you guys verbally through the whole process. But let's plug some numbers in. So I got mass of the block was 1 kilogram. The bullet is 0.01. So there's the combined mass right there. Times square root 2gh. So times square root 2 times 10 times height change is 0.29 meters. If you ever use 9.8 for gravity field, the number would be plenty close enough to whatever multiple choice answer. So it's not going to make that much of a difference. Right? Then divide by mass of the bullet, which is 0.010 kilograms all over again. Okay. 243 meters per second. There you go. That's it. You guys got ballistic pendulum? All right. I got Peyton, Zach, Alexander, Isabel, Elise. Are you guys ready for the win? Ready for the win? All right, here we go. For the win. Ball bounces off the ground. Mass of the ball is 0.5 kilogram. The change in velocity is 20 meters per second. The time of collision is 0.01 seconds. What's the average net force? Should work out to 1,000 newtons. Let's do this over here. Right. So I told you the mass of the ball was 0.5 kilogram. The change of velocity of the ball was 20 meters per second. And the time was 0.01 seconds. Yeah, that's 1,000 newtons average net force. You see it? Okay. But before I show you guys the podium, we're going to see who won the Kahoot. But before that, let's do a 2D version of this real fast because I want to do this especially for my AP students. Let's bounce a ball off the wall, but give you guys an X and a Y axis. See if you guys get this. So there's a wall. Here's the normal line to the wall. I'm going to throw a ball. Here's a ball right here. Let's call it mass of 0.15 kilograms. Make it a baseball. Right. Say this is coming in at some speed. Okay. And boing bounces off. We'll make it an elastic collision. Just keep it easy. Let's say this is 10 meters per second, and it rebounds boing with 10 meters per second. Let's make this angle 60 degrees. This is also 60 degrees right here. Right? Right. So, what else do I have to give you? I have to give you the time interval of collision. Bam. Let's say this time interval of collision is like 0.01 seconds. Okay. So what was the force from the wall on the ball? Okay. So in 2 dimensions, do you think the fact that momentum is a vector and impulse is a vector and force is a vector, we have to consider y direction versus x direction? And in terms of the y direction, nothing actually changes. The ball just keeps on going. Right? Maybe the wall is frictionless. Right? But in the x direction,
there's that normal force, which pushes in the x direction. And that changes the motion of the ball. The ball completely rebounds the opposite direction. So let's consider what's going on in the x direction versus what's going on in the y direction. Now, in the y direction, there's no change at all. But in the x direction, it completely reverses, kind of like you threw the ball straight at the wall and boing, goes back. So, guys, what is this velocity right here? What is this right here? Is it 10 sine 60? 10 sine 60, right? Come on here. So 10 sine 60. I'm looking at, this is 8.66 meters per second towards the ball. And then by symmetry, this would be 8.66 meters per second away from the ball. So guys, what was the change in velocity of the ball? It'd be 17.3 meters per second. Goes heading the ball at the ball about 8.5. It bounces back 8.5 the other way. Guys, what's the difference between 8.5 and negative 8.5? It's 17. You see that? Right. So finally, let's do force, this average net force, times the time interval results in mass times change in velocity. Okay. So I got a mass of 0.15 kilogram right here. This in. Got a change of velocity right there. Divided by the time interval right there. That gives me a force of 259 newtons, about. There you go. All right, let's see who won Kahoot. Who won Kahoot? Got with the bronze, Alexander. With the silver, Isabel. And the gold, Elise. All right, that is a wrap on the review. All right, you guys have a good night and do well on your first period exam tomorrow.